You believe you live somewhere ordinary, not your street, not your country, your cosmic address, the patch of universe your galaxy drifts through, the local sky, the volume of space around you reaching hundreds of millions of light years in every direction. You assume it is a fair sample of the whole, average, the kind of place that could be anywhere. It is not. In 2013, 3 astronomers sat down to count galaxies. Keenan, Barger and Cowie measured the light arriving from galaxies across a range of distances, working in the near-infrared, where the true mass of a galaxy is easiest to read. They expected the count to thicken steadily as they looked farther out, the way a sparse crowd fills in as you walk toward the heart of a city. Instead, the count stayed thin. Too thin. For an immense distance in every direction, there were simply fewer galaxies than there should have been. We are sitting inside a hole. Not a black hole. Nothing is dragging us toward a center, a void, a stretch of space scoured emptier than the cosmic average, where galaxies thin out and the dark between them runs wider than the rules permit. They named it the KBC void, after the 3 who found it. Some call it the local hole. It measures roughly 2 billion light-years from one side to the other. If you shrank the entire observable universe down to the size of a city, this empty patch would be a whole district of it. And the Milky Way sits not at the edge of that district, but close to its middle. Saying that out loud breaks something. Modern cosmology rests on a quiet promise that you are not standing anywhere special, that beyond a certain scale, the universe smooths into sameness and no observer gets a privileged view. A void 2 billion light-years wide, with us near the center, is the exact opposite of a fair sample. By the mathematics that governs how matter spreads across the cosmos, a hole this size has no business being here, and we have no business being in it. If you enjoy these journeys into the strange and the cosmic, hit subscribe and settle in. What follows is a slow walk out to the edge of the emptiness we have been calling home. Here is what turns a curiosity into a crisis. Run the numbers, and a void this large and this deep should appear in a universe like ours almost never. One team measured the disagreement with standard cosmology at 6 sigma. Physicists declare a discovery real at 5 sigma, the bar a new particle must clear before anyone will announce it. 6 sigma is past that line. The emptiness around us should not be here. And it gets stranger, because living inside a hole like this would make the whole universe appear to expand faster than it truly does, which means the void may be quietly bending one of the most carefully measured numbers in all of science. We will get to exactly how a region of almost nothing manages to do that. The cosmic web is the largest pattern there is. Picture the universe not as galaxies thrown across the dark at random, like spilled salt on a black table, but as something with a shape. A vast, 3-dimensional structure that looks unnervingly like the inside of a sponge. Galaxies do not drift alone. They gather along immense filaments of gas and dark matter, bright rivers of material that stretch for hundreds of millions of light-years. Where 2 filaments cross, galaxies pile into clusters. Where many filaments braid together, they build the densest addresses in existence, superclusters holding thousands of galaxies in a single gravitational grip. And between the threads, there is almost nothing. This is the part the pretty pictures never quite prepare you for. The cosmic web is mostly web in name only. By volume, the universe is overwhelmingly empty. The glowing filaments and the bright clusters are the thin borders of enormous bubbles of vacancy, and those bubbles take up the lion's share of all the space there is. Somewhere around 80% of the universe, measured by sheer volume, is void. The galaxies you can see are clinging to the walls of holes. Everything luminous is a rind around an emptiness. So a void in itself is nothing to be afraid of. A void is the most ordinary thing the universe makes. The night sky you grew up under is stitched from them. The question is how the holes got there, and the answer runs all the way back to the first fraction of a second after the beginning. In the earliest universe, matter was spread out with almost perfect evenness, a hot fog of particles smoothed to a sameness we can still measure today. Almost perfect. Not quite. Tiny ripples threaded through that fog, regions that were a hair denser than their surroundings, and regions that were a hair thinner. The differences were absurdly small, fractions of a percent. But gravity is patient, and gravity does not forgive an imbalance. Here is the engine that built everything. A region with a little extra matter pulls a little harder. Pulling harder, it draws in more matter from around it, which makes it denser still, which makes it pull harder again. The rich grow richer, and the regions that started a hair too thin lose the tug of war. Their matter drains away toward the denser places, slowly, over billions of years, until what is left behind is scoured almost clean. The dense places became filaments and clusters. The thin places became voids. The web is simply what gravity does to a nearly smooth beginning, given enough time to work. Let that sit for a moment. The emptiness is not a failure of the universe to put matter somewhere. The emptiness is the matter leaving. Every void is a place that exported its galaxies to its neighbors and kept the dark. We are not guessing at this. Across the last few decades, astronomers built enormous three-dimensional maps of where the galaxies actually are. The 2-degree field survey charted the positions of around 250,000 galaxies. The Sloan Digital Sky Survey, working from a single telescope in New Mexico, has now pinned down the locations of millions more, deep enough into the sky that the maps reach back across a good fraction of cosmic time. And when you render those maps, the web appears exactly as the theory said it should. Filaments, clusters, walls of galaxies, and between them, the great dark bubbles, right where gravity should have carved them. The consensus that came out of all this is genuinely beautiful, and it held for a long time, and most of it still holds now. The picture is this. Step back far enough, and the lumpiness averages out. Up close, on the scale of a single galaxy or a single cluster, the universe is wildly uneven, all light and shadow, all crowding and vacancy. But zoom out, and the unevenness is supposed to wash away. Take a box of the universe 1 billion light years on a side. Weigh everything inside it, and you should get the same answer, no matter where in the cosmos you put the box. Same density, same mix of filament and void. Every fair-sized sample of the universe should weigh about the same as every other. That promise has a name and a scale where it is supposed to kick in. Cosmologists call the scale the end of greatness. It is the size beyond which the universe runs out of bigger things to build. You can climb the ladder of structure for a while. Stars gather into galaxies. Galaxies gather into groups. Groups into clusters. Clusters into superclusters. Superclusters into the long filaments and the walls. But the ladder has a top. Somewhere past about 1 billion light years, the building stops. There are no superclusters of superclusters. There is no structure of structures climbing forever. Above that scale, the theory promises, the universe finally goes quiet and smooth and featureless, the same in every direction and from every vantage. To feel why that matters, hold the full size of things in your head for a moment. The observable universe is about 93 billion light-years across. If you shrank that entire span down to the length of a single human stride, the end of greatness would be a feature smaller than the width of a fingernail. Past that fingernail's width, in this shrunken picture, the universe is supposed to be perfectly, boringly even. No lump bigger than the fingernail, no hole bigger than the fingernail, just smoothness, all the way out to the edge of sight. This is the bedrock. Almost every number modern cosmology has ever produced sites on top of it. The age of the universe, the recipe of ordinary matter and dark matter and dark energy, the rate at which everything is flying apart. All of it assumes that we are looking out from an ordinary spot, a fair sample, a place no different in its broad strokes from anywhere else you could have been born. The whole enterprise rests on the quiet confidence that the patch of universe around us has nothing special about it at all. And for the most part, the universe has cooperated. The maps came back looking like the theory. The cosmic background glow came back astonishingly smooth, even across the whole sky, which is exactly what you would expect if the cosmos really is the same everywhere. Decade after decade, every time someone checked, the principle held. The universe looked fair. Convergence like that is the strongest signal a science can have. Different instruments, different teams, different methods, different wavelengths, all arriving at the same picture from different directions. When that happens, you stop treating an idea as a guess and start treating it as a foundation. By the turn of the century, the smoothness of the large-scale universe was not a hypothesis anyone lost sleep over. It was a thing you built on top of without checking, the way you trust a floor. But there was a thread hanging loose, and it had been hanging for a surprisingly long time. The maps that confirmed the web were maps of the far universe, the deep sky, the galaxies sitting at vast distances. Nobody worried much about the immediate neighborhood, because why would the neighborhood be strange? It is just the nearest sample of an even cosmos. So when a handful of astronomers, going back decades, turned the same counting methods on the galaxies closest to home and tallied what was nearby, the result was treated as a footnote. The local count came up light. Not catastrophically light, just short. When you counted the galaxies in our own corner and compared the tally to what the deep sky said the average should be, our corner had too few. There seemed to be fewer galaxies around us than around a typical spot in the universe. The first hints of it showed up as far back as 1990 in optical surveys that almost nobody outside the field ever read. The numbers were noisy, the samples were small, and the easiest thing to do with an inconvenient measurement is to assume the next, better measurement will make it go away. It did not go away. Each time, someone counted more carefully, with a better instrument, across a wider stretch of sky. The local shortfall held. Our patch kept coming back emptier than it had any right to be. And a few quiet voices began asking the question that, by the rules laid out in this chapter, should not even have been askable. They began asking whether the place we live is a normal place at all. That question is the loose thread. In the next stretch, 3 astronomers and a near-infrared sky survey are going to pull it, and the whole comfortable picture of an ordinary cosmic address is going to come apart in their hands. The thread got pulled properly in 2013 by 3 astronomers who were not hunting for anything dramatic: Ryan Keenan, Amy Barger, and Lennox Cowie. Keenan was the lead, then working from an institute in Taipei. Barger and Cowie were veterans of deep sky astronomy at the University of Hawaii and the University of Wisconsin, the kind of researchers who spend whole careers counting faint smudges of light at the ragged edge of what a telescope can resolve. They had been circling this question for years. 2 earlier papers, in 2010 and 2012, had already turned up the same uncomfortable hint. The local universe looked thin. So they set out to measure it carefully and settle the matter, and they published the answer in the Astrophysical Journal under a title as dry as the finding was strange: Evidence for a 300 megaparsec scale underdensity in the local galaxy distribution. Strip the language down and the title says one thing: there is a hole around us, and it is enormous. The method matters here, because the hole claim lives or dies on it. You cannot simply look up at the sky and notice that galaxies are sparse. The sky is deceptive. A nearby region with few galaxies and a distant region packed with them can throw almost the same amount of light at your telescope, because the distant ones are dimmed by sheer remove. To measure whether your neighborhood is genuinely underpopulated, you need a fair head count of matter at each distance, and you need it to be honest about the stuff that actually weighs something. That is why they worked in the near-infrared. Visible light is a liar when it comes to mass. It is dominated by a handful of hot young stars that burn blue and bright and brief, and it gets soaked up and scattered by dust. Near-infrared light comes mostly from the old, cool, settled stars, the ones that make up the bulk of a galaxy's mass and outlast everything flashier. Count a galaxy's infrared glow, and you are near enough weighing its stars. Weigh the stars across a patch of sky, and you have a usable proxy for how much matter is really there. Near-infrared is the closest thing astronomers have to a scale you can put the universe on. So that is what they did. They built a catalogue of around 35,000 galaxies, drawing the bright nearby ones from an all-sky infrared survey, and the fainter distant ones from deeper surveys with names like Euclid SS and the Sloan Digital Sky Survey. The nearby sample alone covered 90% of the entire sky and was almost completely accounted for. 98% of the galaxies it should contain, all present and measured. This was not a thin slice of the heavens squinted at through a keyhole. This was most of the visible sky, weighed. Then they did the thing that mattered most. They measured how much galaxy light, how much stellar mass, sat in each shell of distance as they moved outward from us. Close in, a little farther, farther still. If the universe is the fair, even place the textbooks promise, that density should be flat. The same amount of matter per unit volume at every distance, near or far, because every sample is supposed to be a fair sample. A straight, boring line. The line was not flat. Close to home, the density of matter was low. As they pushed outward, it climbed. And it kept climbing, shell after shell, until somewhere around 1 billion light-years out, it finally leveled off and stayed level, all the way to the edge of what they could measure. The far value is the true cosmic average, the honest weight of a fair box of universe. And our local value, the density right here where we live, came in far below it. By their measurement, the region around us holds something like half the matter a normal patch of the cosmos should. Briefly, half the galaxies. An apparent shortfall of 46%, give or take 6. Read that again, slowly, because it is easy to let it slide past. They were not describing a small dip in a far-off corner of the sky. They were describing the place you were sitting in. The shortfall extends outward in every direction to a radius of about 1 billion light-years, which means the hole around us is a roughly spherical region close to 2 billion light-years from rim to rim. To put a number that large in any kind of human reach, the entire observable universe is about 93 billion light-years across, so this single hole spans better than 2% of everything there is to see in every direction at once, with us somewhere near the middle of it. This is the thing the script is actually about. They gave it a name, or rather the field did, stitching their 3 initials into it, the KBC void. Some astronomers prefer the blunter label, the one that does not let you hide behind initials. They call it the local hole. I find that second name harder to shake. A void is an abstraction, a thing out there in the catalogue. The local hole is an address. It is the answer to the question of where you live, written at a scale you were never meant to think about. Not the local group of galaxies, not the local supercluster, but the local hole, the great underpopulated bubble that contains all of those and reaches out 1 billion light-years past them in every direction before the rest of the universe finally thickens up to normal. And here is the detail that turns this from a curiosity into something with teeth, a detail Keenan and his colleagues flagged in the paper itself. A local underdensity, they warned, would not just sit there harmlessly being empty. It would distort the very measurements cosmologists use to understand the universe. In particular, they wrote, it could bias what we infer about the expansion of the cosmos and the dark energy supposedly driving it. They saw the danger in 2013 and said so plainly, if we are sitting inside a hole, then the universe we measure from inside that hole is not the universe as it truly is. We would be reading the instrument wrong without knowing it, because the instrument is the sky, and the sky around us is not a fair sample. None of this came out of nowhere, which is part of why it is so hard to dismiss. The local shortfall has a paper trail that runs back decades, long before anyone connected it to a crisis. The first faint signs turned up in optical surveys around 1990. Through the 1990s and 2000s, team after team kept finding the same thing from different angles. Frith and Shanks and their collaborators in England, working in the infrared, kept reporting a deficit in the local counts. A separate group, led by an astronomer named Whitbourne, working with Shanks, found their own version of it, a local void around 15% underdense reaching out a few 100 million light-years. The numbers from different teams did not always agree on the exact depth or the exact size, but they agreed on the direction every time for 30 years. Our patch of universe keeps coming back light. When measurements that stubborn keep pointing the same way, you eventually have to take them seriously. The easy story, the one that lets everyone sleep, is that each underdensity finding is a fluke of an incomplete survey, a corner of sky not yet filled in, a counting error waiting to be corrected. That story works once. It works twice. It does not survive 30 years of independent teams across optical and infrared light, all pulling the local count downward. At some point, the boring explanation becomes the extraordinary one, and the extraordinary claim that we live inside a vast hole in the cosmos becomes the thing that evidence actually supports. There is a real fight over how deep and how wide the hole truly is, and we will get to that fight because it is not settled and the dissenters have a case. But strip away the disagreement over the exact dimensions, and a hard core remains that even the skeptics mostly grant. The local universe is underdense. We are sitting in a region emptier than average. The argument is about how much, not whether. Which leaves the question the whole discovery forces onto the table. The question that should not, by the rules laid out earlier, even be allowed to exist. If the universe is supposed to be smooth past 1 billion light-years, and we have just found a hole 2 billion light-years across, with ourselves near its center, then one of two things is true. Either we have been extraordinarily, improbably unlucky in where we happen to live, or the rule itself, the bedrock promise that no place is special and the cosmos is the same everywhere, is wrong. The strangest thing about the local hole is not its size. It is how long the world managed not to see it. The first hint arrived in 1990, buried in an optical survey that reported the nearby galaxy counts running low. It was a quiet line in a technical paper, easy to file under noise and forget. And mostly that is what happened. But it would not stay buried because other people kept tripping over the same stone. Through the 1990s and into the 2000s, a group of astronomers in England, working largely around Tom Shanks, kept measuring the local sky in the infrared and kept finding the same deficit. Too few galaxies, out to a few 100 million light-years, paper after paper after paper. The signs piled up from every direction. One astronomer counting the very nearest galaxies, within about 150 million light-years, found the local density running 3 to 4 times below what the standard model predicted. Keenan himself had published earlier versions of the result in 2010 and 2012 before the definitive paper in 2013. The Shanks Group eventually gave the thing a name with no jargon to hide behind. They called it the local hole, and they argued it covered most of the sky out to a couple of 100 million light-years. And still, for years, the field looked away. Not out of dishonesty, but out of something more human. The measurement was inconvenient in the deepest possible way. It threatened the one assumption nobody wanted to give up, the assumption that we live nowhere special. And an assumption doing that much work does not get surrendered on the strength of a few galaxy counts. So the result was met again and again with the most reasonable objection in science. Your survey is incomplete. You are missing faint galaxies at the edges. Fill in the gaps and the hole will close. There was real substance to the doubt. Some careful studies genuinely failed to find the underdensity. One major analysis of a large local catalogue reported no hole at all. Others looked for the specific pattern of galaxy motions a void should produce, the telltale inward and outward streaming, and came up empty or found less than the void model demanded. These were not lazy dismissals. They were good scientists reaching different conclusions from overlapping data, which is exactly what a genuine controversy looks like from the inside. The hole was contested because it deserved to be contested. What changed was not really the evidence. The evidence had been accumulating steadily for 30 years. What changed was the stakes. Around 2020, when the Bond Group connected the local hole to the crisis over the universe's expansion rate, the underdensity stopped being a curiosity in a corner of large-scale structure and became a possible answer to one of the biggest open problems in physics. Suddenly, the inconvenient measurement was relevant to everyone, and a result that had waited decades for an audience finally got one. I find that story as instructive as the science. We like to imagine that data speaks for itself, that a true measurement announces itself and the field falls into line. It does not work that way. A measurement that contradicts a cherished assumption can sit in the literature for a generation, correct and ignored, waiting not for better data, but for the field to become ready to hear it. The local hole was visible in the numbers in 1990. We just were not prepared for 30 years to believe what the numbers were telling us about where we live. The hole had been there all along. So had the evidence. What took so long was the willingness to look down and notice the floor was missing. With that history in view, we can turn to the physics of how a hole this large could form at all. So the question becomes how? How does a region 2 billion light-years wide end up scoured to half the normal density? And how do we end up living near the middle of it? To answer that, you have to watch a void being born. And the surprising part is that the process is the same gentle one that built everything else. Nobody hollowed out the local hole. It emptied itself. Go back to the beginning, to the faint unevenness in the early matter. We can measure how uneven because the cosmic background glow carries a fossil imprint of it, and the imprint is astonishingly faint. The hot and cold patches in that ancient light differ from one another by about 1 part in 100,000. Picture a still pond, and on its surface a ripple so shallow it raises the water by the width of a hair across the length of a swimming pool. That is the scale of the lumpiness the universe started with. Almost nothing. A whisper of structure on an otherwise smooth sheet. Gravity took that whisper and ran with it for 13 billion years. The slightly denser patches pulled inward and collapsed. But here is the part that builds the holes, and it gets less attention than it deserves. The slightly thinner patches did the opposite. They did not just sit still and stay empty. They actively emptied further. A region with less than average matter has less than average gravity to hold its contents, so the matter inside it drifts outward toward the denser walls surrounding it, and the region puffs up, expanding faster than the universe as a whole. Underdensity feeds on itself the way overdensity does, only in reverse. The poor get poorer, and the empty get emptier, and a void is simply the long-run winner of that reverse competition. A Soviet physicist named Yakov Zeldovich worked out the choreography of this in 1970, and the picture he produced is still how cosmologists think about it. Matter does not collapse evenly inward like a deflating ball. It collapses first along one direction, flattening into vast sheets, what Zeldovich called pancakes. The sheets then drain along their own length into filaments, and the filaments drain into the dense knots where clusters form. At every stage, matter is leaving somewhere to go, somewhere else. The somewhere it leaves behind, the spaces between the pancakes and the filaments, are the voids. They are the negative space of the collapse, the rooms left empty when all the furniture slid to the walls. We can check this against reality with brute computational force, and we have. Cosmologists build enormous simulations, virtual universes seeded with that same faint initial lumpiness, and then left to evolve under gravity inside a computer for a simulated 13 billion years. The most famous of them, the Millennium simulation, tracked the gravitational dance of more than 10 billion virtual particles. Run the clock forward, and you do not have to tell the simulation to make a cosmic web. It makes one on its own. Sheets, filaments, clusters, and between them, the dark bubbles, blooming out of nothing but gravity, acting on a near-smooth start. The match between the simulated web and the real maps of the sky is one of the quiet triumphs of modern cosmology. The theory does not just describe the universe, it regrows it from a seed. But gravity has had help. and the help only arrived late. For the first several billion years after the beginning, ordinary gravity did the carving on its own, slowly draining the thin regions toward the dense ones. Then, around 5 or 6 billion years ago, something shifted. The expansion of the cosmos, which had been gradually slowing under the collective pull of all its matter, began instead to speed up. The cause carries the name dark energy, a faint outward pressure woven into the fabric of space itself, and today it makes up very roughly 2/3 of everything there is. Dark energy is the great accelerant of emptiness. As the expansion picks up speed, the underdense regions get stretched wider faster than gravity can ever hope to refill them. Matter that might once have drifted back into a thinning patch is instead swept away for good. The voids deepen and widen, and they keep deepening. In fact, this is the very same physics behind the cooling of light we will meet later, the flattening of a void's gravitational valley as space stretches it open. The universe pulling its own empty places wider is the universe chilling the photons that cross them. One process, seen two ways. So a void is not a finished thing. It is a process, still running. The local hole we live in is almost certainly deeper now than it was a few billion years ago, and it will be deeper still a few billion years from now. Zoom out far enough along that trajectory, and the picture turns stark. As dark energy tightens its grip, the bright web will keep thinning. The voids will keep swelling, and the islands of light will find themselves marooned in ever larger oceans of dark. The universe is not drifting toward fullness. It is emptying, slowly and forever. That reframes the hole we live in, and it cuts both ways. On one hand, a deep and enormous void is not some bizarre aberration in a universe ruled by dark energy. It is exactly the kind of thing such a universe is built to produce and to go on producing. On the other hand, all of that deepening, the gravity and the dark energy together, is already folded into the models and the simulations. And even with both engines running at full strength, the standard model still cannot easily make a hole the size of ours. The strangeness is not that the emptiness exists. It is that ours outran even this relentless machinery. Let that sit, because it is the foundation of everything that follows. We are not in the dark about how voids form. We understand the mechanism well enough to recreate it, which means we also understand how big the mechanism is supposed to be able to make them. And this is where the trouble starts. When you run those simulations and tally up the voids they produce, you get a population with a shape to it. Most voids are modest, a few tens of millions of light years across, the kind of bubble the Milky Way could be lost inside billions of times over and still leave room. Bigger voids show up less often. Truly large ones, a few 100 million light years across, are rare. And as you climb toward the largest sizes, the population thins out fast, the way the tallest people in a crowd thin out, until you reach sizes that the simulation, run over and over, simply almost never produces. The universe, according to its own best model, has a ceiling on how empty a place can get and how wide that emptiness can spread. The KBC void sits above that ceiling, a roughly spherical region close to 2 billion light-years across, running about 20% below the cosmic average once you account for everything carefully, possibly deeper. Set that against the simulated population and it lands far out on the tail. In the territory, the model produces so rarely that finding ourselves inside one starts to look less like bad luck and more like a contradiction. To feel the gap, remember that the smoothness scale, the end of greatness, is supposed to arrive by about 1 billion light years, and some estimates place it lower still, which only sharpens the problem. The local hole does not respect that boundary. Its radius alone is roughly the entire scale at which the universe was promised to go featureless, and its full span is twice that. It is not a wrinkle inside the smooth regime. It is a structure as large as the smooth regime itself, which is a sentence that should not be possible to write. There is a way to make the contradiction precise, and the precision is what unsettles people. You can ask the model a direct statistical question. In a universe that obeys the standard rules, how often would a region this large be this empty, just by the ordinary random scatter of where matter happened to clump? The model has an answer, because the size of the expected scatter on these scales is something it predicts confidently. On a span of around 1 billion light-years, the standard model says the density should vary from place to place by only a few percent. A typical patch and our patch should differ by a hair. Instead, they differ by 20% or more. The hole is not a few percent low. It is several times deeper than the deepest dip the model expects to find anywhere. When researchers turned that mismatch into a number, the number was brutal. A team we will meet properly in a moment ran the comparison and found that the observed size and depth of the local hole disagreed with the standard model at the 6 sigma level. 6 sigma is not a casual phrase. Particle physicists hold out for 5 sigma before they will stand up and announce that a new particle is real, the bar that separates a genuine discovery from a statistical accident. 6 sigma is past even that. The odds of a result that's strong happening by pure chance are roughly 1 in 500 million. That is the confidence with which the standard model says this void should not exist, set against the confidence with which the sky says it does. So the universe has handed cosmology a clean contradiction, and there is no comfortable way to hold both halves at once. The mechanism of void formation is sound. The simulations work. The smoothness scale is well measured. And yet here we sit, inside a hole that the sound mechanism, run in the working simulations, almost never makes, larger than the scale at which holes are supposed to stop. Two trusted things cannot both be fully right. Either the measurement of the void is wrong, deeper or wider than it truly is, or something in the standard model of how the universe is built needs to give. Both of those doors lead somewhere strange, and serious people have walked through each. Down one door, the void is real, and the model is incomplete, which means our entire reading of the cosmos has been taken from a vantage point we wrongly assumed was ordinary. Down the other, the void is partly a mirage of incomplete surveys, and the comfort of the standard model survives at the cost of explaining away 30 years of measurements that keep finding the same hole. Neither door is easy. Neither is free. In the next stretch, we open both. We meet the team behind the 6 sigma number and the model they built. We hear the case from the skeptics who think the hole is shallower than advertised. And we follow the consequence that makes this whole argument matter far beyond a debate about counting galaxies. Because if the local hole is real, it does something to the universe we measure from inside it. Something that may have quietly broken one of the most important numbers in science. 3 scientists at the University of Bonn decided to put a hard number on the impossibility. Moritz Hasselbauer, then a young doctoral student, Indranil Banik, a visiting fellow, and Pavel Krupa, the professor who ran their group and who had been needling the field about this underdensity for years already. In 2020, they published a long and careful paper, eventually running to nearly 40 pages, with a title that did not flinch. The KBC void and Hubble tension contradict the standard model on a billion parsec scale. What they did was the obvious thing that nobody had done rigorously. They took the measured void, built a detailed physical model of how such a hole would have grown from a slight initial dimple in the early matter, and then asked the standard model a blunt question. In a virtual universe built on your own rules, how often does this happen? To answer it, they used one of the largest cosmological simulations ever run, a virtual cosmos called the Millennium XXL, big enough to contain a fair sample of regions the size of the local hole. They went looking, in that simulated universe, for a void as large and as deep as the one we live in. They were essentially asking the model to show them a sibling of our home. The model could barely produce one. When they tallied the odds, the disagreement between the observed void and the standard model came out at 6.04 sigma. That is the precise version of the number from earlier, and it clears the particle physicist's 5 sigma discovery bar with room to spare. A 6 sigma result is the kind of confidence that ends arguments and wins prizes. Turned into plain odds, a void this large and this empty should turn up by chance in a universe that follows the standard rules about once in every 500 million tries. We are not supposed to be the one. It gets worse for the standard picture, not better. The Bond team noticed that the void does something sneaky to its own measurement. Because matter is flowing outward off the walls of an underdense region, the galaxies near us carry an extra little kick of motion, and that motion reddens their light beyond what distance alone would cause. The upshot is that the void looks deeper than it truly is. The raw measurement, the 46% shortfall, is partly an illusion created by the outflow. Correct for it honestly, and the true emptiness is only about half that, somewhere around 20% below the cosmic average. You might think halving the number would rescue the standard model. It does not. Even at 20%, even after handing the skeptics every correction they could ask for, the void is still 6 sigma too much. The hole is so far outside what the model can build that you can cut its depth in half, and it remains, by the model's own arithmetic, very nearly impossible. And when the Bond group folded in the separate, well-known disagreement about how fast the local universe seems to be expanding, the combined verdict against the standard model rose past 7 sigma. At that level, you are no longer talking about an anomaly. You are talking about a model that, on these grand scales, appears to be broken. This is the sort of claim that deserves suspicion, and the people making it would be the first to say so. A single team reaching a dramatic conclusion is how science generates excitement, not how it generates truth. So the honest question is whether anyone disagrees, and the answer is yes, sharply, and the disagreement is healthy. The skeptic's case rests on a reasonable doubt. Maybe the void is shallower and smaller than the deepest measurements claim. Maybe the near-infrared counts are tripping over incomplete surveys, patches of sky not yet filled in, faint galaxies missed at the edges. One study in 2022 remeasured the local counts and reported a gentler underdensity than Keenan and his colleagues had found. Other researchers argued that if you look at how the cosmos behaves just past the supposed edge of the hole, the data do not match what a void that size should produce. For a while, it looked as though the whole structure might be a measurement artifact, the kind of thing that quietly evaporates as the surveys improve. But the void has been stubborn under scrutiny. Some of those skeptical analyses were themselves picked apart, their own assumptions found wanting, leaving the underdensity standing. And the single most persuasive thing about the local hole is that it does not depend on any one method. It is not just the near-infrared count. The same shortfall shows up when you survey the sky in optical light, and in X-rays from hot gas in galaxy clusters, and in the faint radio glow of distant galaxies, and in the way the nearby galaxies are streaming. We will come back to that convergence later, because it is the part that makes the whole genuinely hard to wave away. A measurement error in one technique is ordinary. The same hole appearing across the entire spectrum of light, found by separate teams using separate instruments over 30 years, is not the signature of a mistake. It is the signature of something real. A newer line of evidence has only sharpened the picture. Astronomers have a second, independent ruler for the universe, a faint, regular pattern in the spacing of galaxies called the baryon acoustic oscillation, frozen into the cosmos from sound waves in the infant plasma. It is one of the cleanest measurements cosmology has. When researchers tested 2 decades of those measurements against the question of whether we sit in a local void, the data leaned toward yes. A different ruler, a different physics, the same conclusion. The whole keeps surviving the tests designed to kill it. So where does that leave the honest listener, somewhere between awake and asleep, trying to decide what to believe? It leaves you in the uncomfortable, accurate place where the field actually is. The existence of a local underdensity is widely accepted. Our patch of universe is emptier than average, and almost no one fights that anymore. What remains in dispute is the depth and the width, how empty and how vast, and whether the answer is bad enough to break the standard model or merely bad enough to bruise it. The Bond team says, broken. The cautious majority says, wait. Nobody serious says the whole is not there. And the people who say broken have a fix in mind, which is the part that takes this from a quarrel about galaxy counts to a challenge against the foundations of physics. If the local hole is as deep as they measure, then structure in the universe grew faster than the standard model permits, faster than ordinary gravity working on ordinary and dark matter can manage in the time available. To grow a hole that big that fast, you need gravity to reach farther and pull harder on the largest scales than Einstein's equations, fed the standard ingredients, allow. So they reach for a modified theory of gravity, an idea that the rules of attraction themselves change in the weak pull vastness between galaxies. It is a radical move, a minority position, and we will give it a fair hearing later, because if it is right, the emptiness around us is not just a strange address, it is a crack in the law. Step back from the fight for a moment and notice what both sides agree on, because the shared ground is strange enough on its own. We live in a region of the universe that is genuinely underpopulated, on a scale of around 1 billion light-years, near enough to its center that the asymmetry barely shows. That much is not a fringe claim, it is the consensus, and it carries a consequence that neither camp disputes, a consequence the original discoverers flagged on the first page back in 2013. If you measure the universe from inside a hole, the universe lies to you. The emptiness changes how light reaches you, changes how fast the nearby galaxies seem to flee, changes the numbers you write down as the fundamental properties of the cosmos. We have spent a century building a precise account of the universe on the assumption that our vantage point is ordinary. The local whole is the quiet suggestion that it is not, and that some of what we have measured may be a distortion thrown by the shape of the room we happen to be standing in. That is where we turn next, not to whether the whole is real, but to what it does to us for living inside it, and to the one number, more carefully measured than almost any other in science, that the void may have been bending all along. If the local hole is real, at anything like the measured depth, the implications reach a long way past a quarrel between cosmologists, and the first of them is the one the discoverers warned about from the start. Living inside a void changes the number you get when you try to measure how fast the universe is expanding. It does not change the true expansion, it changes the reading. The mechanism is worth slowing down for, because it is so physical, you can almost feel it. We are sitting in a region with less matter than the walls surrounding it, which means the gravitational pull is gentler here and stronger out there, toward the denser rim. So everything in our neighborhood is being drawn, very slowly, outward toward those walls. Not flung, drawn, the way water in a wide, shallow basin drifts toward the drain at the edges. Now add that outward drift on top of the ordinary expansion of the universe, the steady stretching that carries all galaxies apart. Near us, the two motions point the same way. The galaxies around us are not just receding because space is expanding. They are also coasting outward toward the rim. And when we measure their speed and use it to calculate how fast the cosmos is expanding, we cannot easily tell the two apart. The local expansion comes out looking faster than the true global rate. This matters because the rate at which the universe expands is one of the most important numbers in all of science. And for years now, two ways of measuring it have refused to agree. Look at the nearby universe and you get one value. Look at the ancient light from the infant cosmos and you get a noticeably lower one. The gap between them is small in raw terms and enormous in what it implies, and it has become one of the central crises of modern cosmology. A void around us is one candidate explanation, and a clean one, because it would make the nearby measurement read high for exactly the reason just described. That disagreement is a deep story in its own right, with its own cast of instruments and arguments, and it deserves a full night of its own rather than a paragraph here. What matters for us is the shape of the claim. The emptiness we live in may be quietly faking one of the universe's fundamental constants. Sit with that. A piece of nothing, simply by being empty in the right place, could be the reason two of the best measurements humanity has ever made disagree about how the universe behaves. The whole is not just strange to look at. It may be a lens we have been reading the cosmos through without knowing the lens was there. Which brings us to the harder, quieter implication, the one that has nothing to do with any single number. For 5 centuries, the deepest lesson of astronomy has been that we are not special. We are not at the center. Our star is ordinary. Our galaxy is ordinary. Our spot is a fair sample of all the spots there are. That principle is not vanity in reverse. It is a working assumption, and almost everything we believe about the universe is built on top of it, because the only patch of cosmos we can study up close is this one, and we have to assume this one is representative, or we can conclude nothing at all. The local hole does not put us back at the center of creation. Nobody is claiming the old pre-Copernican fantasy that the universe revolves around us. The claim is subtler and, in its way, more unsettling. It is that our particular address is not a fair sample, that we happen to live in a rare, underpopulated pocket, and that we have been doing our cosmology from inside it, mistaking the view from an unusual room for the view from anywhere. We are not special the way our ancestors hoped. We may be special the way a person raised in an unusually quiet valley is special, certain that the whole world is this hushed until they finally climb the ridge and hear the noise on the other side. There is something genuinely vertiginous about that. Not frightening exactly, disorienting. The principle that we occupy no privileged place was supposed to be the one thing we could lean on, the floor under the whole edifice. And the emptiness around us is whispering that the floor might be tilted, just slightly, in a direction we never checked, because checking it required noticing the room. And then there is the plainest implication of all, the one a child could grasp. We have fewer neighbors than we should. If the local count is right, the volume around us, out to 1 billion light years in every direction, holds something like half the galaxies a typical region holds. Half the company. The sky we look up into is emptier than the average sky in the universe, and we never knew, because we have no other sky to compare it to. We were born in the quiet valley, and we called the quiet normal. To feel how much a void can hide, consider an old and humbling thought. There is a famous deep void elsewhere in the sky, and astronomers have pointed out that a civilization living at the dead center of a void that size would have a badly distorted picture of the cosmos. Their nearest galaxies would be so far away, so faint, that they might not realize other galaxies existed at all until their instruments grew very good. They could spend their entire scientific history believing their galaxy was the universe, alone in an endless dark, when in truth they were simply sitting in a hole that hid the crowd. We are not at the center of a void that deep, but we are inside one milder version of the same trap, and the lesson it teaches is the same. What you can see depends on where you stand, and where we stand is not where we assumed. The strangest part, the part that even the people who measured the hole cannot explain, is the simplest question you can ask about it. Why here? Why are we not just inside the void, but close to its middle, in the deepest part of the quiet, as though placed there? In the standard picture, this is pure coincidence, an accident of which galaxy happened to give rise to observers, and coincidences this large are exactly what the standard picture says should almost never happen. There is no mechanism that puts observers in voids. There is no law that says life prefers the empty places. And yet, here we are, near the center of the largest hole anyone has found, asking why. That question has a long shadow, and it touches on whether a universe can look tailored to its observers, which is a road for another time. For now it is enough to hold the discomfort of it. The emptiness is real. We are near its heart, and nobody knows why. Before we go looking at that evidence, it is worth being precise about what exactly would break if the hole is real. Because the assumption under threat is not a vague hunch. It has a name, a history, and a specific mathematical job. And almost everything we believe about the universe is leaning on it. It is called the cosmological principle, and it is the endpoint of 500 years of demotions. Copernicus took the Earth out of the center and put the sun there. Then the sun turned out to be an ordinary star, one of hundreds of billions, sitting in no special part of the Milky Way. Then the Milky Way turned out to be one galaxy among hundreds of billions more. Each discovery shoved us further from any privileged position until the trend itself hardened into a rule. Assume we are nowhere special. Assume the universe looks broadly the same from any galaxy an observer might happen to occupy. The rule became load-bearing in 1917, when Einstein first tried to apply his new theory of gravity to the entire universe at once. The equations of general relativity are ferociously hard to solve for a real lumpy cosmos full of galaxies scattered every which way, so Einstein made an assumption to render them solvable. He assumed the universe is homogeneous, the same density everywhere, and isotropic, the same in every direction. With that single assumption, the impossible mathematics collapses into something a person can actually work with, and out of it came the entire framework of modern cosmology, the expanding universe models that everything since has been built upon. The cosmological principle is not just a philosophical preference, it is the load-bearing wall that holds the equations up. Here is the subtlety that matters, the one that decides whether the local hole is fatal or survivable. The principle does not claim the universe is perfectly smooth. Obviously, it is not. Up close, it is all clumps and voids, galaxies and emptiness, the wild unevenness we have been describing all along. What the principle claims is something weaker and cleverer. It says the universe is statistically homogeneous above a certain scale. Draw a box big enough, and it does not matter where you put it. The contents average out to the same density. The lumpiness is real, but it is supposed to be local, washing away once your box grows past that special size. And that size, you will remember, is the end of greatness, somewhere around 1 billion light-years. This is the Defender's refuge, and it is a fair one. A void, even a large void, need not violate the principle, so long as it is small enough to count as lumpiness below the smoothness scale, or shallow enough to be a rare but a loud fluctuation in an otherwise even cosmos. If the local hole is really only mildly underdense, or smaller than the boldest claims, then the principle absorbs it without flinching. The universe is allowed its bad neighborhoods. One quiet patch does not overturn the rule. And this is exactly why the size of the KBC void is the whole ballgame. 2 billion light-years across is not lumpiness below the smoothness scale. It is a feature as large as the smoothness scale itself, a hole the size of the very box you were supposed to use to prove the universe is smooth. You cannot dismiss it as local texture, because it is bigger than the scale at which the locality was supposed to end. That is what the 6 sigma number is really saying. Not merely that the void is unusual, but that even treated as a statistical fluctuation in a universe that obeys the principle, a hole this big and this empty should essentially never occur. The refuge does not reach far enough to shelter it. So what is truly at stake is subtle, and worse for being subtle. If we live inside a large local inhomogeneity, then the equations everyone has been solving, the ones that assume we do not, give slightly wrong answers when applied to our own measurements. The age of the universe, the recipe of its contents, the rate of its expansion, the strength of its dark energy, every one of those numbers was derived inside a framework that assumes our vantage point is fair. Not wildly wrong, slightly wrong, in ways we cannot easily separate from the truth, because we have only this one vantage point and cannot step outside the hole to check. The danger is not that physics shatters. The danger is that our most precise account of the cosmos has a quiet, uncorrectable bias baked into it, inherited from the shape of the room we measured it in. The principle has earned real trust, and it deserves a fair accounting. Its strongest evidence is the ancient background light of the cosmos, which arrives almost perfectly evenly from every direction, smooth to a few parts in 100,000. That near-perfect evenness is exactly what you would expect if the universe really is the same everywhere, and it is hard to fake. Most cosmologists look at that smoothness and conclude, reasonably, that the principle holds and the local hole must be survivable, a real but tolerable dent in an even cosmos. They may well be right. But a principle is still an assumption, however well it has served, And it was adopted in the first place, not because anyone proved it, but because the mathematics demanded something tractable. That is the uncomfortable thread the local whole tugs on. We assumed we were nowhere special because assuming otherwise made the universe impossible to calculate, and now a whole 2 billion light-years wide is asking whether the convenient assumption was also the true one. Which is precisely why the evidence that the whole is real, gathered across every kind of light, matters as much as it does. If our vantage point is compromised, we had better be very sure the compromise is real before we let it shake the foundations. Most tellings of this story stop at the galaxy counts, the infrared survey, the missing galaxies, the whole. But a single counting method is a single witness, and a lone witness can be honestly mistaken. The reason the local whole has survived 30 years of skeptics is that it does not rest on one witness. It has many, and they testify in kinds of light the human eye will never see, and they agree. Start with the X-rays, because galaxy clusters are the heavyweight champions of cosmic bookkeeping. A cluster is a swarm of hundreds or thousands of galaxies bound together, and trapped between them sits a vast cloud of gas heated to tens of millions of degrees, hot enough to glow in X-rays. That glow is a beacon. It lets you find clusters across enormous distances and, just as important, it marks where the universe has piled up its matter into the densest knots. Count the clusters in a region, and you are taking the pulse of how much matter lives there. A team led by the astronomer Hans Boehringer spent years doing exactly that, building X-ray cluster surveys with names like Reflex and Classics, the latter cataloguing more than 1,600 clusters across 2/3 of the sky. And when they mapped where those clusters sit relative to us, they found the same thing the galaxy counters had found, written in a completely different language. The local region is poor in clusters. By their measurement, the shortfall runs somewhere between 30 and 50% in the cluster count, which translates to a matter underdensity of around 20 to 30% within a few 100 million light-years of us. A separate instrument, a separate physics, the hot gas of clusters instead of the infrared glow of stars, and out comes the same whole. Then there is the radio sky, and here the evidence takes a stranger form. If the universe really is the same in every direction, then the distant radio galaxies scattered across the sky should be spread evenly. Give or take the small lopsidedness caused by our own motion through space. They are not spread evenly. Two physicists, Rubart and Schwartz, measured the imbalance in a large radio survey and found it pointing more strongly in one direction than it had any right to. The lopsidedness was about 4 times larger than our motion alone could explain. Something beyond our velocity is tilting the radio sky, and one clean way to produce that tilt is to sit slightly off-center inside a large local void, so that the universe genuinely looks different toward the rim than toward the far wall. And finally, there is motion, which may be the most telling witness of all, because it does not count anything. It watches. Galaxies are not frozen on the sky. They drift, each carrying a small velocity on top of the universe's overall expansion, and across a large region, those small velocities average into a collective drift called the bulk flow. In a smooth, fair universe, the bulk flow should be modest and should fade as you average over bigger and bigger volumes, because in a fair universe, the pulls from every direction roughly cancel. In 2023, a careful study of the motions of nearby galaxies found a bulk flow that does not fade the way it should. Out to something like 1 billion light-years, the galaxies around us are streaming together far faster than the standard model permits, around 4 times faster than expected, a disagreement that reaches nearly 5 sigma and crosses that mark at the largest scales measured. Think about what that drift means. A whole region of the universe, ourselves included, is sliding in a common direction at a speed the model cannot account for. And a void supplies a natural cause, because matter on the inside of an underdense region is drawn steadily outward toward the denser walls. Exactly the kind of coherent, large-scale streaming the bulk flow studies see. The galaxies are not just sparse around us. They are moving as though something large and empty is letting them fall outward. The whole is not only visible, it is in motion, and we are moving with it. Lay the witnesses side by side, and the case is hard to shrug off. Optical light first hinted at it. Infrared counts measured it. X-ray clusters confirmed it in hot gas. The radio sky tilts in a way it explains, and the very motions of our neighbors trace the outward fall it would cause. 5 independent lines of evidence gathered by separate teams over 3 decades across nearly the entire span of light, all converging on the same conclusion. We live in a whole. I keep returning to that word, convergence, because in science it is the closest thing there is to a fingerprint of truth. Any one method can carry a hidden flaw. A survey can miss faint galaxies. A calibration can drift. A sample can be too small. But the flaws in infrared photometry, and the flaws in X-ray cluster counting, and the flaws in radio sky maps are not the same flaws. They do not share a hidden error that could fake a hole in all of them at once. When wildly different instruments, prone to wildly different mistakes, all report the same anomaly, the boring explanation runs out of room. You are left with the possibility that the thing is simply there. Honesty demands the other side of the ledger, and it is real. Not every analysis finds the whole. A few careful studies, working from the same data with different assumptions, have failed to see the underdensity, or have found the expected inward and outward motions missing where the void model says they should appear. Those nulls are not nothing. They are the reason this remains a live argument rather than a settled fact, and the reason the depth of the whole is still fought over rather than agreed. A responsible account has to hold the descent in view and resist the pull of a tidy story. But weigh the ledger as it stands, and it leans heavily toward a real underdensity. The convergence across the spectrum is simply more than the nulls can offset. The mainstream position has shifted over the years from "this is probably an artifact" to "we likely do live in an underdense region," with the fight now centered on how deep, how wide, and how much damage it does to the standard model. That is a remarkable migration for an idea that began as a footnote in an optical survey nobody read. There is one more way the emptiness gives itself away, and it is the most delicate of all, because it is written into the oldest light in existence. The faint background glow of the early universe has been traveling toward us for more than 13 billion years, and on its way, it has passed through everything that lies between there and here, including the great voids. And passing through a void leaves a mark on it. The mechanism is gorgeous and a little counterintuitive. A photon falling into the gravitational valley of a void picks up a tiny bit of energy on the way in and pays it back on the way out. And in a static universe, the two would cancel exactly. But our universe is not static. Dark energy is stretching it, and that stretching causes the void's gravitational valley to flatten slightly during the very time the photon is crossing it. So the photon climbs out of a shallower valley than the one it fell into. It cannot pay back all the energy it borrowed, and it emerges very slightly cooler than it went in. A void, in effect, chills the light that crosses it. A dense supercluster does the reverse, warming it. The effect even has a name, the integrated Sachs-Wolf effect, after the physicists who worked it out in the 1960s. The cooling is absurdly small, a few millionths of a degree against a background glow that sits a couple of degrees above absolute zero. No single void imprints a chill you could ever pick out of the noise. So astronomers did something clever. They took a catalogue of the largest known voids, dozens of them, and stacked the patches of background light sitting behind each one, averaging them together. The random noise washed out. What remained, emerging from the average like a face from static, was a cold spot. Voids really do leave their fingerprint on the relic light of the Big Bang, and superclusters leave a warm one, exactly as the theory of a dark energy universe predicts. It is one of the most direct confirmations we have that voids are not just catalogues of missing galaxies, but genuine physical structures, deep enough to bend and cool the oldest light there is. And here, one last time, the emptiness does the thing it keeps doing. When the chill was measured, it came out stronger than the standard model said it should, by a few sigma, an excess that has stubbornly survived better data and tighter analysis. The voids touch the light more than the model predicts. We have now seen the same refusal at every scale we can probe. The hole is deeper than the model allows. The dwarf galaxies inside voids are scarcer than predicted. The bulk flow is faster than expected. And even the fingerprint voids leave on the ancient sky is a little too dark. Whatever is going on, the universe's emptiness is consistently, quietly exceeding what our best theory says emptiness is allowed to do. So the hole is most likely real and large, and we are inside it. Which forces a question the convergence cannot answer on its own. If the standard model genuinely cannot build a void this big, then either we are the 1 in 500 million accident, or the model is missing something fundamental about how structure grows on the largest scales. There is an even more intimate way the emptiness has already touched us, and it has nothing to do with measurements or models. The void is not just where we live. It is part of what moves us. Our galaxy is not sitting still. The whole local group, the Milky Way and its companions, is hurtling through space at about 630 kilometers every second relative to the ancient background light of the cosmos. That is more than 2 million kilometers an hour. We are not drifting. We are racing in a definite direction. And for decades, the central question of this particular corner of astronomy was simple. What is pulling us? The first answer was a thing called the Great Attractor, a dense concentration of mass a couple of 100 million light-years away, sitting awkwardly behind the bright band of our own galaxy, where it is hardest to observe. Then astronomers realized the Great Attractor was itself being drawn towards something larger and farther, the Shapley concentration, a colossal supercluster around 650 million light-years off, one of the greatest pilings up of galaxies in the nearby universe. The picture seemed complete. We were falling, with our whole supercluster, toward the heaviest thing in our region of the cosmos. That supercluster has a name now, given to the vast flow we belong to. Laniakea, a Hawaiian word meaning immense heaven, mapped out in 2014 by tracing the motions of thousands of galaxies and finding the watershed within which they all stream toward a common flaw. Laniakea contains something like 100,000 galaxies across 500 million light-years, and the Milky Way sits out near its ragged edge, a single mote being carried along in an enormous, slow river of matter. But the river had a mystery in it. The pull of Shapley and the Great Attractor, when you added it up honestly, did not quite account for how fast we are moving. Something else was contributing, and for a long time, nobody could say what. The answer, when it came in 2017, was as elegant as it was strange. A team led by the astronomer Yehuda Hoffman mapped not just where the galaxies are, but how they flow. And they found that our motion is set, in almost equal parts, by two things. One is Shapley, pulling us toward it. The other is a vast region of emptiness on the opposite side of the sky, pushing us away. They called it the dipole repeller, and the physics behind it is beautiful once it clicks. In a universe where everything attracts everything, an empty region cannot literally push. But relative to the crowded average, a void behaves exactly as if it does. Matter is drawn toward the dense places and away from the empty ones, so a galaxy sitting between a supercluster and a void gets pulled toward the cluster, and in effect, shoved from behind by the emptiness it is leaving. Underdense regions, as the researchers put it, push as much as overdense regions pull. The void does not need a hand to move us. Its sheer lack of matter is the hand. So consider what that means for the place we live. We are inside one large underdensity, the local whole, and our motion through space is driven, half of it, by repulsion from another. The emptiness is not the passive backdrop to our cosmic life. It is an active force, shaping where we are and steering where we go. A region of almost nothing reaching across more than 1 billion light-years to lay its hand on the small of our galaxy's back and press. To put that reach in scale, the flow the team mapped spans over 1 billion light-years, something like 1/10 of the radius of the entire observable universe, all of it organized around the pull of one great density and the push of one great void. We are used to thinking of emptiness as what is left when the important things are removed. The dipole repeller turns that around. Here, the emptiness is one of the important things. It moves galaxies. It sculpts the local flow. It is half the reason our own galaxy is going where it is going. And it raises a thought worth sitting with as you drift towards sleep, that the nothing between the somethings is not inert at all, that the universe is shaped as much by where its matter is absent as by where its matter gathers. That restless motion, the falling and the being pushed, the streaming of a whole supercluster toward its floor, is the sort of large-scale behavior that a small group of physicists believe ordinary gravity cannot fully explain. Which brings us, at last, to the people who think the hole we live in is not just a strange place to live, but a crack in the law itself. To understand why a hole in space would make anyone question gravity itself, you have to follow the logic the Bond team followed. If the local hole is real and as deep as they measure, then the universe carved out a region 2 billion light-years wide in the time available since the beginning. Carving a hole that big means moving an enormous amount of matter off the inside and onto the walls, and moving matter takes gravity, and the amount of gravity ordinary physics supplies, even with dark matter doing its share, is not enough to do the job that fast. Structure in our universe grew quickly. A void this large says it grew faster than the rules allow. And the most direct way to grow structure faster is to make gravity, on the largest scales, stronger than Einstein and Newton say it should be. That is a heretical thought, and it has a name, and the name is older than the void debate by decades. Modified Newtonian dynamics. Most people who use it just say MOND. Mond was born in 1983, the work of an Israeli physicist named Mordechai Milgram at the Weizmann Institute, and it was not invented to explain any void. It was invented to explain a different scandal, one that had been gnawing at astronomers since Vera Rubin's careful measurements in the 1970s. Galaxies spin too fast. Out at the edges of a spiral galaxy, the stars orbit so quickly that the gravity of all the visible matter, every star and every cloud of gas, should not be able to hold them. By the ordinary law of gravity, those outer stars should fly off into the dark. They do not. They stay, circling at a steady, stubborn speed that the visible matter cannot account for. The mainstream answer to that scandal is dark matter. The idea that every galaxy sits inside a vast, invisible halo of some unknown substance, matter that neither shines nor blocks light, but whose gravity holds the spinning galaxy together. Dark matter is the consensus, and it is a powerful one, woven into the whole standard model of cosmology, and most physicists are confident it is real. Milgram proposed something else. What if there is no invisible matter, he asked, and instead the law of gravity itself changes when the pull gets extremely weak? That is the heart of Mond. Newton's law works beautifully where gravity is strong in the solar system, on Earth, anywhere you have ever tested it. But the outskirts of a galaxy are a regime no laboratory can reach, where the acceleration on a star is almost unimaginably gentle, about 100 billion times weaker than the tug of the ground beneath your feet. Milgram suggested that below a certain threshold of feebleness, a specific tiny acceleration he could write down, gravity stops falling off the way Newton said and begins to fade more slowly, reaching farther than it has any right to. Add that single change, and the fast-spinning galaxies need no dark matter at all. Their stars stay in orbit because gravity, out there in the faint, cold edges, is simply stronger than the textbook allows. What makes Mond impossible to dismiss outright is that it works remarkably well at the scale it was built for. Feed it the visible matter of a galaxy, and it predicts that galaxies' rotation with uncanny accuracy across more than 100 galaxies, big and small, bright and dim, with a success rate that has unnerved its critics for 40 years. There is even a haunting coincidence baked into it. The threshold acceleration Milgram needed turns out to be close to a number you can build from the expansion rate of the entire universe, as though the behavior of a single spinning galaxy somehow knows about the cosmos as a whole. Nobody is sure whether that coincidence is a clue or a mirage. So here is the connection the Bond group drew. If gravity reaches farther on large scales, then structure grows faster and voids grow deeper and wider than the standard model can manage. The same modification that keeps the outer stars of a galaxy in orbit would also let the universe scoop out a hole the size of the local hole in the time available. The bulk flow that streams too fast, the void that runs too deep, the structure that formed too early, all of them point, in this reading, to the same culprit. Gravity is stronger in the dark than we think. The emptiness around us is not a fluke. It is the fingerprint of a different law. I want to be scrupulously fair here, because this is a minority position, and the majority has good reasons for staying where it is. Mond has real and serious failures. It works for individual galaxies, but when you scale it up to giant clusters of galaxies, it falls short. Even with the modified law, clusters seem to need some extra unseen mass to hold together, which quietly reintroduces the very dark matter Mond was built to abolish. there is a famous collision of two galaxy clusters. The bullet cluster, where the gravity and the visible matter appear to have come unstuck from one another. The gravitational pull sitting where invisible mass would be, rather than where the glowing gas is. To many physicists, that single image is close to a smoking gun for dark matter and an embarrassment for modified gravity. And the ancient background light of the universe, the faint pattern frozen into the infant cosmos, is fit beautifully by the standard model with its dark matter and very awkwardly by MOND. The Bond team has answers for some of this. Their model is not bare MOND, but a hybrid, modified gravity, stitched together with a particular flavor of lightweight neutrino to handle the clusters and the background light, an attempt to keep the successes while patching the failures. Whether that hybrid hangs together is exactly the kind of question that takes a generation to settle. Most cosmologists are not persuaded. They suspect the local hole is shallower than the boldest measurements claim, or that some refinement of dark energy and dark matter will absorb the anomaly without tearing up the law of gravity. That is the safer bet, and in science the safer bet usually wins. And it is worth laying out why dark matter is the safer bet, fairly and in full, because the case for it is far broader than one galaxy's stubborn spin, and a story that gives MOND a hearing owes the mainstream the same. The idea that most of the universe's mass is invisible did not start with rotation curves. It started in 1933, when an irascible Swiss astronomer named Fritz Zwicky measured the galaxies in a distant cluster and found them moving so fast that the visible matter could not possibly hold the cluster together. By every law of gravity, the cluster should have flown apart long ago. Something unseen was binding it. He called the missing stuff dark matter, and then the field ignored him for 40 years. When the evidence finally caught up with Zwicky, it came from every direction at once, and that convergence is the heart of the case. Start with light bending. Mass warps space, and warped space deflects passing light, so a heavy foreground object distorts the images of galaxies behind it like a lens. Map the distortion, and you map the mass, whether or not the mass shines. Do this across the sky, and you find far more mass than the visible galaxies can account for, vast invisible halos cradling every cluster, exactly where the motion said unseen matter should be. Then there is that collision of clusters, the one MOND struggles with, and it deserves a closer look because it is close to decisive. When two galaxy clusters smash through one another, the ordinary matter, which is mostly not stars but the hot gas between them, collided and slowed and piled up in the middle, glowing in X-rays. But when astronomers mapped the gravity using the lensing trick, the mass was not in the middle with the gas. It had sailed straight through, out ahead with the galaxies, as though most of the matter barely felt the crash at all. That is the signature of dark matter, a substance that passes through itself like a ghost because it interacts through gravity and almost nothing else. The mass and the visible matter came unstuck, and a modified law of gravity, which ties the pull to where the visible matter is, has a very hard time explaining how. The deepest evidence, though, is written in the oldest light there is. The faint background glow of the infant universe is not perfectly smooth. It carries a pattern of slightly hotter and cooler patches, the frozen imprint of sound waves rippling through the primordial plasma. The exact sizes and brightnesses of those patches depend with exquisite sensitivity on how much ordinary matter and how much dark matter the early universe contained. Measure the pattern and you can read off the recipe. The recipe that fits demands roughly 5 times as much dark matter as ordinary matter. And separately, The cosmic abundances of the lightest elements, the hydrogen and helium forged in the first few minutes, pin down how much ordinary matter exists, and it falls far short of the total the gravity requires. Two completely independent measurements, the ancient light and the primordial chemistry, agree that most of the matter is not the kind we are made of. There is one more, and it bears directly on this whole story. Structure itself needed dark matter to form in time. The cosmic web grew from those faint early ripples, but ordinary matter could not begin clumping until the universe had cooled enough to let it, hundreds of thousands of years in. Dark matter, blind to light, felt no such delay. It could start collapsing earlier, building the gravitational scaffolding into which ordinary matter later fell. Without that head start, the simulations cannot grow a cosmic web as rich as the one we see in the time available. The very filaments and voids we have been marveling at may owe their existence to the invisible scaffold that shaped them. Lay all of that side by side, and you see why most physicists will not trade it away. Cluster dynamics, gravitational lensing, the colliding clusters, the ancient background light, the primordial elements, the growth of structure itself, all of them pointing to the same unseen mass, each prone to different errors, none of them sharing a flaw that could fake the result across the board. It is the same kind of convergence that makes the local whole hard to dismiss, turned to the opposite purpose. The one great embarrassment is that after decades of searching, no experiment has ever caught a particle of dark matter directly. We infer it everywhere, and have touched it nowhere. And that absence is the crack Mond keeps trying to pry open. But here is the twist that matters most for our story, and it cuts against the easy assumption that this is a fight between dark matter and modified gravity. The local whole is a problem even if dark matter is completely real. The 6 sigma calculation was run inside the standard model, the one with all its dark matter included, and the void came out nearly impossible anyway. So the emptiness around us does not simply pit one theory against the other. It strains the model whichever side you take. You can believe wholeheartedly in dark matter, as most cosmologists do, and still be left staring at a hole the universe should not have been able to make. That is what gives this anomaly its weight. It is not a weapon in someone's pet theory. It is a problem for everyone. But not always does the safer bet win. The history of physics has a handful of moments where a stubborn anomaly that everyone expected to dissolve instead turned out to be the loose thread that unraveled an entire worldview. A small shift in the orbit of Mercury that Newton could not explain became, in Einstein's hands, the death of absolute space and time. Nobody knows yet whether the local whole is a Mercury or a mirage. What we can say is that serious people, looking at the same emptiness, have concluded that the simplest way to explain it is that our deepest law of attraction is incomplete. They may well be wrong. But the fact that the question is even on the table, raised by a hole in the sky we happen to live inside, tells you how much weight this quiet emptiness has come to carry. Whichever side is right, the argument will end the way every argument in this science ends. Not with a clever theory winning a debate, but with better maps. And the better maps are arriving now. The whole case for the local whole was built from surveys that, by modern standards, were squinting. Tens of thousands of galaxies, large patches of sky, real but coarse. The instruments now coming online work at a different order of magnitude entirely. In the deserts of Arizona, an instrument built to measure dark energy is collecting the spectra of millions of galaxies, fixing their distances precisely enough to map the local density field with a sharpness no previous survey approached. From space, a European telescope is charting the shapes and positions of billions of galaxies across a third of the sky, building a three-dimensional census of where matter sits across cosmic time. And in the mountains of Chile, a telescope has opened its eye that may settle the question on its own. It is named for Vera Rubin, the astronomer whose measurements of spinning galaxies started the whole dark matter argument half a century ago, which is a fitting circle, because her observatory may help decide whether that argument needs reopening. It carries the largest digital camera ever built, more than 3 billion pixels, and it will photograph the entire southern sky every few nights for 10 years, cataloguing billions of objects and watching the universe change in something close to motion. To grasp that haul, every previous map of the local cosmos we have discussed was assembled from a few tens of thousands of galaxies. This one observatory will gather billions, turning the core sketch of our neighborhood into something approaching a photograph. With maps that fine, the questions that have hung over the local whole for 30 years become answerable. How deep is the underdensity exactly? How far does it reach? Are we near its center or off to one side? Does the local expansion really run fast in the way a void would explain? Or does the effect vanish under closer scrutiny? Is the bulk flow as strong as the boldest studies claim? Each of those is a measurement, not a matter of opinion, and within a decade we should have the numbers clean enough to know. There is something fitting about that, and something humbling. The whole was found by counting what was missing, with instruments that could barely make out the gaps. It will be confirmed or dissolved by instruments that can count nearly everything there is. Either the emptiness around us will firm up into one of the genuine cracks in modern cosmology, a real challenge to the assumption that we live nowhere special, or it will soften into a modest dip, large but survivable, and the standard model will absorb it and move on. We are right now in the last years of not knowing. But here is the thing that no map, however fine, will resolve. Even when we have measured the whole to the last decimal, when we know its depth and its width and our exact place within it, the deepest question it raises will still be standing. Knowing the precise dimensions of the room does not tell you what it means to have woken up inside it. That question is not for the telescopes, it is for us. There is a famous void in the sky, and it is not ours. In the direction of the constellation, Boötes lies an emptiness so stark that when astronomers first mapped it in 1981, they called it the Great Nothing. It spans about 330 million light-years, a region the Milky Way could be dropped into and lost billions of times over, almost entirely free of galaxies. When it was found, the result was so extreme that some astronomers suspected an error in the survey. There was no error. Across a volume where thousands of galaxies should sit, only a few dozen do, scattered so thinly that they barely register as a structure at all. For decades, it was the poster child of cosmic emptiness, the whole everyone pointed to. And that is exactly the point about it. We point to it. The Boötes void is something you observe from the outside, a distant curiosity sitting safely 700 million light-years away, a hole in someone else's sky. The local hole is the other kind of emptiness. You cannot point at it because there is no direction to point. It is behind you and in front of you and above and below, in every direction at once, because you are inside it. The Great Nothing is a thing we found. The local hole is a place we live, and it dwarfs the famous one. Set the two side by side, and Bhutas is a pond beside an ocean, a few 100 million light-years against 2 billion. Put it in terms of sheer volume and the gap is starker still. Double the width of a sphere, and you multiply the space inside it eightfold. So a hole 2 billion light-years across does not hold a little more emptiness than one a few 100 million across. It holds hundreds of times more. The entire famous Great Nothing, the void that frightened the astronomers who found it, would fit with room to spare into a small corner of the quiet we are sitting in. The void that made the textbooks is the small one. The one that might break cosmology is the one we never noticed, because noticing it meant noticing the shape of home. That brings us to the deepest consequence of all, the one that outlasts every argument about depth and width and modified gravity. For a century, humanity has been building an exquisitely detailed account of the universe, its age, its ingredients, the proportions of ordinary matter and dark energy, its rate of expansion, the whole magnificent edifice of modern cosmology, accurate to a few percent, the pride of the science. And every brick in it was laid on a single unspoken assumption, that the place we measured from was an ordinary place. If it is not, the edifice does not collapse, but it trembles. The discoverers said as much on the first page in 2013. A local hole, they warned, would bias the very cosmological measurements we treasure, and they pointed in particular at the expansion rate and at what we infer about dark energy from the nearby universe. The reasoning is the one we have already met. We build our measurements outward from the local cosmos, rung by rung, like a ladder. And if the bottom rungs sit inside a hole that distorts distance and motion, then everything we stack on top inherits the distortion. We would not be measuring the universe. We would be measuring the universe as seen from the bottom of a well, and mistaking the warped view for the thing itself. I want to be careful not to overstate this, because the temptation is to say the void explains everything, and dark energy was a mirage all along. It does not, and it was not. The strongest evidence for the accelerating universe comes from light that left its sources long before it ever reached the rim of our hole. From depths the void cannot touch, and that evidence stands. The local hole does not abolish dark energy. What it threatens is subtler and more insidious. It threatens the precision. It introduces a doubt into the numbers we quote, with the most confidence, a quiet asterisk on measurements we believed were clean. And in a science that now argues over differences of a few percent, a quiet asterisk is enough to keep people awake. This is what the title was really pointing at. The largest empty space in the universe should not exist by the rules we wrote, at the size we find it, with us near its center. That sentence sounds like a fact about something far away, a record-breaking object in a catalogue. It is not. It is a fact about your address. The strangeness is not out there. The strangeness is the ground you are standing on, the local sky you were born under. The patch of cosmos you have always assumed was as ordinary as any other. The biggest thing wrong with the universe might be the part of it you live in. And even if the skeptics are right, even if the hole is shallower than the boldest measurements and the standard model survives intact, the lesson does not fully retreat. Because the doubt has been planted now, and it cannot be unplanted. We know that our vantage point is at least somewhat unusual, at least somewhat emptier than average. And we know that we assumed otherwise for 100 years without checking. The exact depth of the hole is still being argued. The fact that we never thought to ask whether we were in one is not. That is the part that stays with me. Not that the universe is strange, but that the strangeness was sitting underneath us the whole time, and we only found it by counting the galaxies we did not have. So we are left holding a discovery that refuses to resolve into comfort. The whole is real, almost certainly. Large, probably. Deep enough to break the rules, possibly. And ours, without question. Whatever the final measurement says about its depth, it has already done the irreversible thing. It has turned the sky from a window into a wall and shown us that we have been reading the cosmos from inside a room whose shape we are only now beginning to trace. The galaxies we can see are the far side of that room. The emptiness is the room itself. And the last question, the one that no telescope and no theory can answer for us, is not about the whole at all. It is about what it means to be the kind of creature that lives in one and notices and has to go on living anyway. We have spent this whole journey treating the emptiness as a problem, a number that disagrees with a model, an anomaly to be explained, a crack to be patched. But before we leave it, step inside it, because a cosmic void is not the featureless black nothing the word suggests. It has a texture and a kind of life, and knowing what it is like in there changes how it feels to live in one. Start with the obvious correction. A void is not empty. It is rarefied, which is a different and stranger thing. The deepest voids hold less than 1/10 of the average density of the universe, but 1/10 of something is not nothing. Drift through one and you would pass thin clouds of diffuse hydrogen, a scattering of dark matter spread too thinly to clump, and here and there, separated by gulfs that beggar the imagination, a lone galaxy. In a dense cluster, you might find hundreds or thousands of galaxies packed into a region. In the heart of a void, you might find a single galaxy, adrift in several million cubic light-years of near vacuum. The void is not the absence of a universe. It is a universe stretched almost to transparency. And it is not smooth either. When astronomers look closely at the interiors of voids, they find a faint filigree, a ghost of structure, tenuous subfilaments and gossamer walls threading the emptiness like the inside of a soap bubble, catching the light. Voids contain smaller voids. They have a hierarchy, a nested architecture that is the fossil record of how they formed. The debris left as smaller emptinesses merged into larger ones over billions of years. The void is not a hole punched in the cosmos. It is a delicate, almost skeletal structure in its own right, the negative image of the bright web, with an anatomy you could spend a career mapping. The galaxies that live in this rarefied world are different, and that is one of the most beautiful findings in this whole subject. Astronomers built something called the Void Galaxy Survey, a careful study of around 60 galaxies that live deep inside voids, chosen specifically because they grew up in isolation. And these void galaxies do not look like their crowded cousins. They tend to be smaller, lighter, bluer, richer in raw hydrogen gas, still busily forming new stars long after galaxies in denser neighborhoods have settled into middle age. They are, in a real sense, younger at heart, slower to evolve, more pristine. The reason is loneliness, and it is worth dwelling on. A galaxy in a crowded region lives a violent life. It is forever falling into clusters, colliding with neighbors, getting its gas stripped away and its shape mangled, its star formation switched on and off by the gravitational chaos around it. A void galaxy is spared all of that. With no near neighbors to disturb it, it simply drifts, holding on to its gas. forming stars at its own unhurried pace, preserving the character it had in the early universe. The emptiness is not cruel to the galaxies that live in it. It is gentle. It lets them keep their youth. There is one void galaxy that has stayed with me since I first read about it, catalogued under a plain survey number, a quiet disk of stars that astronomers describe as among the most isolated objects in the nearby universe. Try to picture the sky from a world inside it. On a clear night, you would see your own galaxy stars, the same dense river of light we call the Milky Way. But turn your telescope outward, into the dark beyond, and there would be almost nothing for an enormous distance. No bright neighboring galaxies hanging in the black. No companion smudges to map. Just an immense, patient emptiness. And somewhere out at the very limit of detection, faint as a candle across an ocean, the nearest other island of stars. A civilization on such a world would have to work much harder than we did to learn that it was not alone. Our own astronomers found the neighboring galaxies with the telescopes of a century ago. Theirs might need instruments far beyond that, just to confirm the universe did not end at the edge of their own starlight. The emptiness would not only shape their galaxy, it would shape their imagination, their sense of how full or how barren the cosmos is, their first guess at whether anyone else was out there. Where you were born decides what questions even occur to you. And here is the turn that brings it home. The standard model predicts that voids, though poor in big galaxies, should still swarm with tiny dwarf galaxies, thousands of faint little smudges sprinkled through the emptiness. When astronomers go looking, they find far fewer than the model promises. The void interiors are even emptier than they are supposed to be, missing not just the giants, but most of the dwarfs as well. It is a modest puzzle with a famous name, the void phenomenon, raised decades ago and never fully resolved, and it is one more small place where the universe's emptiness refuses to behave the way the theory says it should. The holes are deeper than predicted, quieter than predicted, lonelier than predicted, at every scale anyone has checked. Now hold all of that against the fact at the center of this story. We are not watching void galaxies from the outside the way the surveys do. We are, in a gentler sense, among them. Our own neighborhood is underdense. The Milky Way is not buried in the deepest part of the deepest void, nothing so extreme as the isolated worlds the surveys study. But we live in a region thinned out below the cosmic average on a scale of 1 billion light-years. In the long catalogue of galactic environments, ours leans toward the empty end. We are mild void dwellers, and we always have been, and it left fingerprints we are only now learning to read. Maybe that is why our own galaxy has had the relatively quiet history it has. Fewer catastrophic mergers than a galaxy in a denser place might suffer. Enough stability over enough billions of years for a steady star and a steady world, and the slow business of life to unfold without being thrown into the fire. And here, caution matters, because no one can claim the void made us. That is a story we do not have the evidence to tell. But it is not nothing to realize that the emptiness we have been calling a problem is also the environment we grew up in, the quiet field in which our particular galaxy got to live its long, undisturbed life. The texture of the void, then, is not the texture of a void at all, not in the bleak sense. It is rarefied, structured, gentle, slow. It preserves what denser places destroy. It hides the crowd and keeps the quiet, and the more carefully you look at the emptiness around us, the less it resembles a flaw in the universe, and the more it resembles a particular kind of place, with its own character, its own population, its own way of shaping the things that form inside it. We came into this looking for what was missing. Half the galaxies gone, a density that should not be this low, a hole that should not be this big. And all of that is true, and all of it still presses on the foundations of cosmology. But somewhere in the long counting of the absent, the emptiness stopped being only a subtraction and started being a setting. Not the nothing between the somethings, the room itself, the wide, still room in which we happen to wake up. Return, one last time, to where we began. You believe you live somewhere ordinary. That was the flaw under everything, the hard-won humility of 5 centuries of astronomy. Do not imagine you are special. Do not place yourself at the center. Assume your corner is a fair sample of the whole, because that assumption is the only thing that lets a small creature on a small world say anything true about the universe at all. The emptiness around us is the cosmos quietly declining that assumption. Not by putting us back at the center of creation. The old vanity is gone for good. By something stranger. By revealing that the place we drew our maps from is itself unusual, a vast underpopulated hush, and that we mistook its quiet for the quiet of everywhere. We were the child in the silent valley, certain the world was this still, because we had never stood anywhere else to hear it. Think about what had to happen for us to find out. Matter had to drain from this region over 13 billion years, leaving it half as full as the cosmic average. A galaxy had to form anyway, in the thinning, with a star ordinary enough and patient enough to hold a warm world steady for the billions of years it takes for awareness to wake up. And then that awareness had to look outward and count, and notice that the count came up short, and have the nerve to follow the shortfall to its impossible conclusion. The whole did not announce itself. We had to subtract our way to it, galaxy by missing galaxy, until the absence took shape. There is something I keep turning over in the quiet. We tend to think of emptiness as the absence of things that matter. But the emptiness we live in is not the absence of the universe. It is the part of the universe that let us see the rest. A more crowded sky might have blinded us, drowned the faint and distant in the glare of the near. Our hush is what made the long view possible. The local whole is not the universe withholding itself from us. It may be the room, dark and wide and still, in which the universe finally grew quiet enough to be noticed. That is the reframe worth carrying off to sleep. The void is not a wound in the cosmos. It is an address, and it is ours. And it is the only place that has ever asked these questions, because it is the only place where someone happened to be listening. The standard model may bend around it. Gravity itself may have to be rewritten to make room for it. The argument will run for another generation, and the answer, when it comes, will not change the simple fact underneath. We woke up inside a great quiet, and we named it, and the naming is the most remarkable thing about it. So when you next look up, know what you are looking through. Not a clear window onto an even cosmos. The inside of a hush 2 billion light years wide, with you near its center. The galaxies thinning away in every direction, like lights seen across an enormous dark field. The matter left long ago. The silence stayed. And in the silence, something opened its eyes and counted what was missing and understood for the first time exactly where it was. near the center of the emptiest place we have ever found, home.